is now blinking, and it hasn't been blinking. So if you really need the video, I can put the next class in there. Okay, so I did something on purpose, folks. Okay, I did something on purpose. I did not define for you this idea of relative maxima and minima because I wanted you to see if you could get it intuitively. Okay, but if you go back to the bottom of this page, you will see the definitions. So let's take a look at the definitions. Oh, I forgot, I froze this. Let me unfreeze this. Okay. Now notice it says when a function changes from increasing to decreasing at a point called c f of c. So here's our function. I'm increasing until I get to this point right here, whose coordinates are c f of c. And at that point, I now start, decreasing. So notice by the very definition, you have to have something on some values of your function on either side of that point called c f of c. Okay, so you have to have your value defined to the left of c and to the right of c. There has to be some function there. So when you go from increasing to decreasing, this is called the relative maximum. It occurs at x value equal to c, and the relative maximum value is the output. So if this point was, let's say, 10, 150, the relative maxima would be 150. I'm only interested in the maximum outpoint value, my maximum, say, weight that I'm going to achieve, 150 pounds. Wouldn't that be nice? But anyway. All right, so 150, that's the relative maxima. It occurs at when I was 10 years old, all right, at x equals 10, all right? So I just made that up, I know. I was a fat kid, what can I say? All right, so, but notice right here is really important language, folks, because you came across it in a minute ago. Your function changes from increasing to decreasing, so you have to have something on both sides of your function. So when you come to this point here, right here, where a lot of you were debating at your tables, is this point a relative maxima point? It's not changing from increasing to decreasing because there's nothing on the other side of it, to the left of it. So you don't even look at that point in terms of relative maxima or minima. What about this point, 2, 5? Is your function defined to the left of 2, and it's increasing, and then it's decreasing? So books use different words. Another word for relative maxima, which I like better, is local. So you could say relative maxima or local. And the reason why I like local a little bit better is because you just find the point you're interested in and you look in the neighborhood. So if you just come down to the neighborhood on either side of this point 2, 5, the maximum value in this neighborhood from, say, x equals 1 to x equals 3, that's the local neighborhood around that point. 5 is the top dog in this neighborhood, right? 5 is the maximum value in the neighborhood. So it's relative. It doesn't mean it's the maximum value, the absolute maximum value this function can take on, because guess what? This function has no absolute maximum because it goes off to infinity. So just in this neighborhood, if I blew that up, 5's going to feel like the big fish in the little pond, right? So 5 is the relative maxima or local maxima. Okay. Well, some people in their neighborhoods don't feel like the kingpins. They feel sort of like the serfs, right? The people that have to go and work for the kingpins. Now I'm starting to sound like Gangsters of New York here. All right. So, oh, that is the name of a movie. All right. Oh, let's pick on one from Boston. What was the name of that one in Boston with Matt Damon and? Oh yeah, what was it? What was it? Never mind. All right. So in this local neighborhood, Departed, right? And that's where my accent is from. So in this local neighborhood, -3, -2, that point would be considered where the, now this is important, where the relative minima occurs. The relative minima is -2. It occurs at x equals -3. When I ask for relative minima or relative maxima values, I'm interested in the output value. If I ask you where it occurs, you can say, hey, it happens to occur at -3. So we have two relative minima. We have a minima value right here, a low point, and we have a minima value here, a relative minima value here. We have one relative maxima. This is not a maxima, relative maxima, because there's no function defined to its left, so you can't say it's increasing or decreasing. Okay, so let's go down here. Any relative maxima and the numbers at which they occur. So the relative maxima is 5, and it occurs at x equals 2. That's how we would fill that in. No, I don't want the coordinates. I want the absolute relative maxima value. The relative maxima is 5. That's the output. When you see this, we want output only.
So I'm saying for
Occurs at x equals 2. It occurs at an x value, not at a 2 coordinates. Okay? So here's your output, which is what you typically call your y value, and where it occurs is what you typically call your x value. Any relative minima and the numbers at which they occur. We have a relative minimum value at -2 and 0, and they occur at x equals -3 and x equals 5. And then these last two, I think, are intuitive. All right, so the last thing we have to cover for this section, and then the final piece of section 2.2 we're going to cover on Wednesday. Cecilia? That's at 6? Yes, we don't know. It occurs, like, in other words, thank you for mentioning that. So, well, I should have probably. So in other words, we're trying to figure out what the values are when f of x is 6, right? We know one of the points is x equals -7. So the other point we would have to estimate, right? So if we continue this curve like that, could we estimate approximately where it occurs? What point do you think that might be? 8, right? So this occurs at x equals -7 and x equals 8. Okay, thank you. Okay, even and odd. Are you even or are you odd? Well, let's take a look at this. We call this function even, and one way you can think about it is think about making a paper crease right along the y-axis. So you're going to fold that paper, your paper, right along the y-axis, right? And when you do that, if there's a point on you, and this is where I was going to show you that interactive figure that it's not working. Here's a point on the right side, 2.5. What is the output at 2.5? -14.44, okay? Unfortunately, we're not going to be able to fill in this table because that figure isn't working. And I don't have the equation, but I can basically show you what would have happened. Notice, if I take a point on the other side of the y-axis equidistant from 0, that's its opposite, notice its value is also at -14.44. Okay, now what we were going to do was we were going to fill in this table, and I was just going to sort of move this x and its opposite all along the x-axis. So let's just pretend for a minute. If I moved x into, say, 1, if x was 1, what would be the output? 0. If I move to the opposite of 1, which is -1, what is its output? 0. So notice if I take a number and then I go on the other side, I take its opposite, my output remains the same. Okay, so let's go up here. Let's suppose x is right here now at 3. What's my y value at 3? Here I am at x equals 3. What's my y value approximately? 15. Okay. If I go to my opposite, negative 3, I come up, I'm still at 15. Okay. Yeah. Okay. So the definition of an even function is that if I took this blue function and I folded it along the y-axis, every point to the right of 0 would have a matching point to the left of 0. They would be like kissing cousins, because when you fold them, they're right on top of each other. Okay? They're symmetrical, right. Supposedly, if you drew a vertical axis down through our face, we have symmetry, but no face has perfect symmetry. If you ever look at pictures of people, sometimes the eyes are a little different, sometimes the one nostril's a little high. I mean, there's always, but one of the quote unquote definitions of beauties is how symmetric or even symmetry your face has. All right? I won't get into definitions of beauty. That's for your sociology class. Okay. So what is the definition of an even function? Here's how we write it mathematically. If you put in x and if you put in its opposite, the output values are exactly the same. No matter where I go to the left and right, my points have exactly the same y values. That's an even function. Let's take a look at an odd function. Here's an odd function. We say it has symmetry about the origin. Notice, here's my x value right here, 1.28. My output value is 12.13. Now I go to x's opposite value. Am I still up here at 12.13? No, I've moved down to its opposite. So when we have symmetry, odd symmetry, we have symmetry about the origin, and that means the distance from this point to the origin is exactly the same as from the origin to this point. They're both the same. They're congruent, the distances of those lines. So a linear function is the opposite. Yep. When you put in opposite values, your output are opposite. Notice our output, oops, our outputs here. This is okay. Sorry, folks. There's a typo here. At 1.28, we're 12.13. Oh, I'm right. I'm trying to hurry because I just looked at the clock. Okay. So the input when you're 1.28 and the output at negative 1.28 is not the same. They're different. They're opposites. And that's what this says. When I put in two opposite values, my output is opposite. Cecilia? Show me after, because I got to let folks go. Okay, so your exams are up here. I do want to make one or two comments. If you could just give me 30 seconds before you pack up, please. Now, I put 2 scores at the top of the exam. You might see a score like this, which represents it might be in blue or black. And then over here in green is another score. Let's say, this is your exam score. This is your course, your grade average to this point. Okay, can you get that door for me, Alexis? Now remember, and what I did is I graded everybody as if they were test light. I know some of you will be test heavy, and you can let me know anytime between now and the end of the week, and I'll adjust your grade. Remember, to get this grade, this one exam is counting what percent? What exam for test light? What percentage is your exams for test light? 40%. So that means when you have 3 exams, each exam is going to be 13.3%. Right? Every exam will be 13.3%. So this exam is only going to be 13% of your whole grade in the end. But today, is it weighted heavily? Yes, because you have no other exams. So if you did in either direction, if you did great on the exam, then this is weighted, skewed more to the positive side. If you didn't do great on this exam, then this is skewed a little bit more to the lower side. Don't freak out. You have plenty of time. So if you did very well, whatever you're doing is working. If you didn't do so well, that's a sign to say, Linda, we need to get together this week and let's see what else I can do. Okay? Life is not over. Life isn't great on either end. Overall, my two classes did very well for what I call the first exam of the semester. The median was 77, which meant half of the students that took this did better than 77 and half did less than 77, which isn't bad for a college algebra exam. Okay, thank you. I'll get you, where are they? Right here. I think it's on your schedule, which is where I have most dates, right, folks? Does it say we have a quiz? Okay, so these are in alphabetical order. Taylor, Jonah, Brendan. And please don't assault me now, folks. I have 5 minutes before I have to get to the studio, and I need to start recording. See me in my office. Haley? Karis, please do not assault me now, I said, okay? Karis? Ian? I'll see anybody in the studio if you want to talk to me. Kyle? Orlando? Sonia? Eric? Ryan? Julia? Eric? No, Logan? Logan's not here today. Cecilia? Curtis? Curtis, here's your project. Liza? Joe? Jojo? Alex? Andrew? Nathan? Tiffany? Did you just hear what I said? Could you see me in the studio, please? I've got to close up, get my stuff together, and then go in the studio.